useful to find the velocities of points on the manipulator and then find static forces. Okay, what we're trying to do is trying to find the velocity of the end point. To begin with, we'll do the end point end effector, but then I'll show you how to find the velocity of any point on the manipulator. So this is the the homogeneous matrix which defines the position of the end effector and the orientation of the end effector. And so if you take the first derivative of the position, you get the velocity. And then if you want to find the rotation or the angular velocity, then you need to take this R matrix and multiply it in a specific way, which we did in a previous class, and you get S. Okay, so this computation can be done. It's very likely when you do it, you'll get a giant mathematical expression, which is not very wealthy. So we try to make it easier for you to do this computation. And so what we're going to do is we're going to try to express the velocity as JV, which is the Jacobian of the velocity, times Q dot. Q dot is the degrees of freedom. So theta dot, theta 1 dot, theta 2 dot, or D1 dot, D2 dot, everything clumped together as a matrix. We'll also try to find the angular velocity as J omega times Q dot. Okay, so this is our goal, to find the relation between V, omega, and Q dot. And so I started off with computing J omega last time. Okay, there's a derivation which gives me the angular velocity as JW times Q dot, where Q dot is the degree of freedom, and J omega is basically this expression. You can see from this expression that only involves R1, R2, 0, and so on. All these matrices, R1 and so on, are easy to compute because those flow from the DH matrix, the homogeneous matrix associated with the DH. Rho 1, rho 2, rho 3 are specific to the joint. So if it's a prismatic joint, then rho is 0. If it's revolute, it's 1. So that's super easy, convenient to do. Let's try to do the same thing for JV. Okay, and I started off doing this last time, but I couldn't complete it. So I'm going to pick up from here. And you got to understand this derivation, at least the intuition behind it, in order to eventually solve problems. Okay, so that's why I'm not just writing down the formula, but deriving the expression. So we need to derive the formula for JV for a prismatic joint as well as for a revolute joint. That's what we'll do right now. Okay, so let's do it for the prismatic joint. Okay, before I do that, actually, let me backtrack a little bit. Okay, before I actually derive the formula. Okay, so let's look at this formula which I derived earlier. Essentially, it is looking at the velocity formula, which I wrote down earlier, is the derivative of the position of the end effector. And what I did was I used the partial derivative to expand that out. That's straight from calculus. There's nothing with related to manipulator there. Okay, so I can write that down as this expression times q dot. So this is JV. Okay, now from this, there's something very simple which you can do, which is if you set q1 dot equal to 1 and everything else equal to 0, then you'll see that the velocity of the end effector is simply don dq1, right? Okay, so what this is saying is, but this thing here is JV. I would call it the first element. It is the first element of JV. So if you want to find JV, what you have to do is set a unit motion to Q1 dot, set everything else to 0, and that will give you JV1. If you want to find JV2, you would set this equal to 0, Q3 and so on to 0, put Q2 dot equals 1, and that will be JV2 would be VON, VQ2, VN0. So everything over here is going to tell you about the end effector motion in terms of the JVs, provided you set the right coordinate to 0. So what I'm going to say here is, we observe that Vn0 equals JVI when Qi dot is set to 1 and every other joint rate is set to 0. So this is going to be very key in the derivation I'm going to just do. Okay, it just follows from the math. Okay, so let's now use this to find JV1. This is the base of my manipulator. There's a prismatic joint somewhere in the manipulator chain. Could be link 1, link 2, it could be joint 1, joint 2, some link. Let's call it I. And let's say the motion of this link is in the upward direction. So that should be Zi minus 1 actually, because that is joint I minus 1. The motion for this joint is Di. This goes by convention. And if you want to know more about this, this is joint I minus 1. Okay, so the base link or base joint has a series of links which I've not shown. I've only shown a link joint I minus 1. And I'm going to show the end effector, which is the joint connected to joint N. And this is my end effector. So since I've denoted the end effector as ON0, I'll call it ON0. Okay, I'm going to draw a few vectors. One from here all the way to ON, so that's ON0. That is the meaning of ON0. It basically gives you the position of the end effector with respect to base frame. That way. And then I'm going to draw a straight line from link joint I-1, or the origin of that coordinate frame connected to joint I-1 to O. Okay. Now, if you remember, I just said JVI is basically DON DQI when DI, or in this case it's going to be DI, DI, Q is equal to I, equals 1, and other DOFs have 0 speed or 0 velocity. But that is also equal to the velocity of the end effector. Okay, so in order to find JVI associated with that link, I need to essentially look at we write it like this, TD. That's right. Okay, so now there's this. Okay, so what I'm interested in doing is I'm trying to move the joint DI, or I-1 through a unit distance along ZI-1, so DI dot equals 1, and trying to see what happens to the end effector velocity. So when I move the joint upwards, right, because that's the way the joint would move, ON would also move in that same direction upwards along ZI-1. So the motion of, or the velocity of the end effector, which is ON0, is going to be along the ZI-1 direction. Okay, but that is the velocity, sorry, that's the motion. So ON dot has a magnitude and a direction. Since this is unit velocity, I have di dot equals 1. It's going to be the magnitude times ZI-1. But if you're trying to look at what's the velocity when what's the velocity of the end effector when this is not equal to 1, it is some generic value, then it's simply ON dot equals the magnitude, which is di dot, times ZI-1. So magnitude times direction, but you can write a formula for ZI-1. ZI-1 is Ri-1 times K. So why is it Ri-1 times K? Because K is a vector along the Z direction. What this does is basically isolates the K component of Zi-1. This coordinate, there's a coordinate frame here, X, Y, Z. Say Z has to be this way, X, I-1, Y-1, and then Z is this way, Zi-1. So in order to find at Zi-1, I need to take the rotation matrix which relates the frame I minus 1 with respect to frame 0, and then find the k component. That's why I multiply it with k. Anyway, so from these two things, from these two expressions, you can write JVI equals ZI minus 1, which is RI minus 1, 0K. So you don't want to remember, you just want to remember this expression. This is all you need. This should be JVI. A different color for this. So JVI, this is for a prismatic joint. Okay, let's do the same thing for a revolute joint. Find an expression for JVI. It's the same, going to be the same argument. Case B, revolute joint. Okay, and somewhere there is a revolute joint in the chain Zi minus 1. Associated with this is a rotation theta I, and then I keep going to reach the end effector. It's my ON0. This is OI minus 1, and I'm going to connect a few things. There's a vector here which defines the distance of ON from the origin, and this vector here which defines OI minus 1, 0. Okay, and following a similar reasoning, I need to set theta I dot equals 1 and all other rates equal to 0 to get JVI equals DOI D, in this case theta I, and then theta I dot is equal to 0. So you won't write that down. So it equals to 1, sorry, write that down, which is the same as the velocity of nth link, which is equal to O. Okay, so if I want to find this formula, I need to find what happens to the end effector, which is defined by ON0, when I do a unit velocity, give a unit velocity to theta I. Okay. So when I turn theta I by unit velocity, the question is how would ON0 move? Okay. So the velocity of ON is given by this well-known formula for velocity as a function of speed, which we have derived. Not derived, we've actually used it quite a few times before. This is simply the omega angular speed crossed with r, where omega and r should have the right convention. So this is the formula for the linear speed. Linear speed is always omega cross r, and so omega in this case is going to be the rotation of the joint I crossed with, well, the rotation of that joint. I just can't put the rotation as magnitude. I need to put the magnitude and the direction. The direction is going to be along zi minus 1, right? Because it is going giving me in this rotation about zi minus 1 crossed with the vector from r. This r vector goes from here to here. This is r. It's from the end effector n to the point oi minus 1. And if you remember vector rules, this is basically a triangle, a closed triangle. ON0 equals R plus OI minus 1. And so if you want to find R, you need to subtract ON0 from ON minus 1. So this would be ON minus OI minus 1. Now we've said this is equal to 1 because that's how we defined the Jacobian, right? The angular velocity theta dot equals 1. So we are left with this formula, JVI equals ZI minus 1 crossed with N0 minus O I minus 1, but ZI minus 1 equals RI minus 1 0 K, same as before the previous formula, ON0 minus OI minus 1 0. So this is the expression for the Jacobian of a revolute joint Okay, so we've defined the Jacobian for the velocity for revolute joint. So I'm going to basically summarize what we did in the last class and this class. So list of formulas which we'll be using to solve problems. So here is a summary of all the formulas. JV, which is the Jacobian associated with the velocity, is equal to Ri minus 1 K crossed with O n minus O I minus 1 for a revolute joint. It is equal to Ri minus 1 with respect to frame 0 times K for a prismatic joint. The Jacobian associated with the angular velocity equals Ri minus 1 0 K for a revolute joint. This we did last class, and then 0 for a prismatic joint. So we'll be using this, but this might be very handy to remember. If you want to find K, which comes many times here in this expression, K is simply 0, 0, 1. It's the unit vector in the z direction. You'll also need to find Ri minus 1 0 K. Okay, which is basically it takes the R matrix. The R matrix you can get from the TH table. You have the R, the 3 by 3, the first 3 by 3 elements are the R matrix, and then there is the ON part. So R1, R2 1, R2, R3 1 should be R1 2. 2 2 R3 2 R1 3 R2 3 R3 3, and when you multiply with K, which is 0 0 1, you'll see that you get something as simple as R1 3 R2 3 R3 3. So you do not have to do this math. I already did this math for you, which is the Ri minus 1 times K is basically the first 3 rows of the third column of ai minus 1 0, right? Ai minus 1 with respect to frame 0 is something which you would compute given a DH table. We've done that numerous times. So all you got to do is look at the ai minus 1 0, look at the first 3 rows of the third column, and that's your r, I minus 1 0 times k. If you want to find on, okay, this is going to be the first 3 rows of the fourth column of an0, because we know that the A matrix has the R times the end effector coordinates. So you have to search for the end effector coordinates from the A matrix. And then OI minus 1 0 is the first 3 rows of the fourth column of AI minus 1 0. Okay, and we'll actually keep using this, so that hopefully when I do this repeatedly for at least 3 problems today and next class, you'll get used to. Okay, consider the 2-link manipulator. It's a planar manipulator. We've done so many times now. Point P at the end of the right. Okay, it should be second link. And point C is midway on the first link. Okay, so P is the end effector, C is midway in the second link, first link, sorry. Find the Jacobian for point P and Jacobian for C. Okay. And I've given you the DH table. If you don't have the DH table, you'll have to get that before you can solve this problem, because it involves the A matrix. Okay, so let's do this one at a time. So let's start with A, the Jacobian of the point P. It has 2 parts to it. There is a JV part and a J omega part. So what will happen is, since there are 2 links, you will have 2 JVs. So let me call that JV1 and JV2, and you'll have 2 J omegas. So this will always depend on the number of links. Depending on the number of links, you'll have so many J's. So the first step is try to figure out what JV1 is. JV1 is basically the Jacobian associated with point P. In this case, point P is of interest, which is the end effector, when you have a unit velocity to 1 and 0 velocity to 2. So this is a Revolute joint, and so we need to hunt down the formula for a Revolute joint. So if we go back to my summary, we see that we are looking at a Revolute joint and we are looking at JV. So this is the formula where N is going to be the end effector, right? So that's what I'm going to put down for JV1. So R, in this case, I equals 1 because the first link, K cross. Now ON0 is what was originally there, but ON0 is simply the position of the end effector, which is this point. It actually is O20, this is O10, and this is O0. So O20 minus O, here I had written I minus 1 with respect to 0, but I is 1, so O00. For JV2, that is the Jacobian when you give unit velocity to 2, keep theta1 dot equal to 0, and that also is a Revolute joint, theta2. So use the same formula except you replace I with 2 instead of 1. So same formula, I minus 1 is going to be 1, with respect to 0, k crossed with again the position of the end effector, so O to 0 minus O I minus 1, so it's going to be 1, 0. We should just write this formula here so it's less confusing. This is R I minus 1, 0, k crossed with O n 0 minus O I minus 1, 0. Okay, the next one is the Jacobian associated with the angular velocity. And we're talking about a Revolute joint theta. So let's go back to the summary. J omega we need for the Revolute joint, so it's R I minus 1, 0, k. Pretty simple. I'm going to write this down. So I need to use R I minus 1, 0, k over here and here, and so that's simply replacing I with 1 and 0, so R 0, 0, k and R 1, 0, k. That's all. Okay, so once you do this is probably the hardest part. Everything else after this is pretty much crunching numbers. That is essentially writing A10, A00 and then figuring out those values. So let's find A00. If you recollect, this is R10, sorry, my bad. This is R00, 0, D00, 0, sorry, 1. Okay, for A00, whenever you have 0 with respect to 0 or 1 with respect to 1 or 2 with respect to 2, this matrix is always an identity matrix. This is always true. Next, A10. Okay, we'll have to use the DH formula. So DH formula goes by the DH table. So you'll replace the elements for link 1. And when you put it in the formula for the DH, you get C1 minus S1 0 A L1 C1 S1 C1 0 L2 sorry L1 S1 then 0 0 1 0 0 0 0 1, where C1 is cosine theta 1, S1 is sine theta 1, and then A21, which again comes from the DH formula, is C2 S2 L2 C2 L2 S2 0 1. C2 is cosine theta 2, S2 is sine theta 2. This expression comes from use DH formula. Okay. We need to do something else. We need to find A20 because R20. We need A20 because we have O20. So I'm going to write an expression for A20, which is A10 times A21, and both these A10 is available right there, A21 is available right there. So you to multiply these two, I recommend using MATLAB. And you also have to use a command called simplify so that it actually puts it in the simplest form. The simplest expression for this is actually quite simple. It's not that hard. C12 S12 0 0 minus S12 C12 0 0. L1 C1 plus L2 C12 L1 S1 plus L2 S12 0 1, where C12 is cosine theta 1 plus theta 2, S12 is sine theta 1 plus theta 2. Okay, so once we get this, which is purely a mechanical process. You don't have to think much, use MATLAB. We are now in a position to find JPQ because we have access to all these things we need. So let's write these things down quickly. Okay, so let's start with R00K. Okay, R00K is first. So I'll write it down slowly here just so that you can, it's easy for you to understand what's going on, but eventually I'll not write in words. So it's the first three rows of the third column of A00. Okay, so if you go back and look at the first three elements of the third column, that is equal to R00K. So we put that here. 001. So we need R10. So similar to this is the first three rows of the third column of A10. So let's go back and check what that is. So first three, not this, my bad, this one. First three rows of the third column of A10. So let's write that down. We also need O20. So O20 is first three rows of the fourth column of A20. So let's find that out. Let's go back to A20. This is A20. This is the fourth column, and there are three elements. So first three elements of the fourth column. So that's going to be O20. Similarly, this is going to be, sorry, not this one, my bad. But this one, this first three elements, three rows of the fourth column of A10 is going to be O10, and then this is O00. So I'm just going to put all these three things on the page so that you have a ready reference. So O20 is going to be L1C1 plus L2S12 L1S1 plus C12 L2S12 0. O10 is L1C1 L1S1 0, and O00 is equal to 0, 0, 0. So you can write that's for A00. Okay, so right now I have everything I need in order to find this, all these things. They're all there, written down everything. So it's just a matter of crunching numbers in MATLAB. Okay, so this step which you can do it in MATLAB. And you should totally try this because sometimes it's hard for people to do this. Try to put these values in MATLAB and get the answer. So this will give me a matrix which looks like this: L1, L1, S1 minus L2, S12, L1, C1 plus L2, C12, 0 minus L2, S12 minus plus L2, C12 and 0. Okay, and 0, 0, 1, 0, 0, 1, where this part is JV1, this part is JV2, these last three are J omega 1, this is J omega 2. So this matrix is 6 cross 2, and it has elements like so. So that is just a math thing. You want to try to do this using MATLAB. Okay, we're done with part 1. Now the second part is slightly tricky, but actually much simpler than the first one. We got to find the Jacobian of Q, where if you recollect, Q is this point, midway on link 1. Okay, so again, because this is a two-link manipulator, it would have JV1, JV2, J omega 1, J omega 2. So I'm going to write the formulas for the Revolute joint because there are only Revolute joints in this case, so I don't need to actually have this full table of Revolute and prismatic. For Revolute joint, we've seen that JVI is R I minus 1, 0, K crossed with O N 0 minus O I minus 1, 0, and then J V omega I equals R I minus 1, 0, K. Now, one thing you want to remember is when we derived the formula for Jacobian, this was for the end effector. That is, we are finding the Jacobian of the end effector. In this case, we are not told to find the Jacobian of the end effector, but it is some point on link 1, right, C. So what will happen is this thing over here will be replaced with the point of interest. So for end effector, that's fine, but in this case, it's going to be position of C. So for the first one, for the first element, JV1, again, the interpretation is what is the motion velocity of C when theta 1 dot equals 1 and theta 2 dot equals 0, right? So when theta dot 1 moves by unit, how does C move? It would move by a formula given by that. So I'm going to write down R00K crossed with OC0 minus O00, because I just replaced the end effector position with C because I'm no longer trying to find the Jacobian of the end effector. The next one is JV2, okay, and you want to pay attention here. So JV2 is the angular speed, or sorry, it's the velocity, linear velocity of point C when theta 1 dot equals 0 and theta 2 dot equals 1. Now, if theta 2 dot moves, but theta 1 does not move, then C is not going to move, right? This is at rest. This is moving by unit velocity, but C is not on that link, it's on the first link. So motion over here will not affect the motion of point C. So C cannot move, so it's actually 0. So you cannot just blindly write down that formula. You have to think about Jacobian in terms of these motions. In fact, if the point is near the base frame, you see multiple rolls will become zero just because they do not induce motion in. So motion away from the joint will not induce motion in links which are close to the joint, and so there will be multiple zeros if you're told to find Jacobian this way. Okay, next let's move to j omega 1. Okay, here again we're trying to find what is the angular velocity of point C when there's unit motion in theta 1 dot and no motion in theta 2. You got to use that formula. That's R00 K. And again, same thing. If theta 2 dot moves, but theta 1 dot does not move, C will not move. And clearly the velocity of, angular velocity of C is going to be unaffected. So that's going to be 0. Okay, so this is because motion of theta 2 does not affect motion, effect does not lead to motion of C. It does not. So in this formula here, I in fact have computed this in the previous problem, this one. The only thing which is, this is 0, 0, 0. Only thing missing is OC0. I need to find OC0. Once I find OC0, I'm done. I can then sub it in that formula. So how do I find OC0? OC0 is the position of C with respect to the base frame. Okay, and you can figure that out from trig, right? It's basically going to be, this length is L1 divided by 2, and so x component is going to be L1 divided by 2 cosine theta 1 and L1 divided by 2 sine theta 1 for the y. But you would not want to rely on trig, because if it's a complicated manipulator, then it's going to be hard to do that. So you can actually use your A matrices, the A's we derived, to find that. Let's do it in a different way. I'm going to, do I have space here now? So let's find OC. Let's find or evaluate OC0. Okay, so I'm going to redraw the manipulator. This is the brace frame. This is point C. It's at a distance of L1 divided by 2. It's at a distance of L1 divided by 2. Okay, so let's, how do we find AC0, OC0? Okay, so one thing to note is when this frame is fixed to the link, the second link, and as the manipulator moves, theta 1 changes, x1 moves with it, right? So what I can do is I can write an expression for OC0 as A10 times OC1. Okay, what is OC1? It's the position of C in frame 1. Okay, frame 1 is shown here. That's frame 1. And the only reason I did this is because I observed that as the first link moves, or x1, y1 moves, C will keep moving and it will be at a fixed distance from the origin of this frame. Okay. However, its position from 0 will change. So A10 is something we have derived I written down earlier. I'm just going to copy paste it here. Okay, let's write OC1. Now this is, as I said, the position of C in the frame 1. Okay, you got to look at where is this point when you look at this frame. You can see that that point C is along the x1 axis. It's along the x-axis, right? It's negative x1 axis. So I'll write minus L1 divided by 2 because it is at a distance of L1 divided by 2 from along the x1 axis. Its y coordinate on the x, that is along y1, is 0 because it's along the x-axis, and then 0, 1. So when I multiply those two matrices together, you will see that you get something like this: L1 C1 divided by 2, L1 S1 divided by 2, 0, 1. Okay, which by trig we figured out that is the right answer, right? L1 cosine theta 1 divided by 2, L1 sine theta 1 divided by 2 is the right expression for point C from trig, and so that agrees. Anyway, so once you get this, you can write a formula for J. JCQ. It's a little bit of math. I highly encourage you to try doing this yourself using MATLAB. Don't try to do hand calculation. So the 3 parts, or the 4 parts of the matrix. Top left corner. You mean this one? Yeah. What I did was I put in this value here, then I took R10K, which is, I think it's 001. It's basically 001, I think. Let me check. I think that's incorrect. It should be 00. This should be, I copied it wrong, right? That's the formula. Yeah, that's the formula, so I got it wrong, that formula. But let's see what happens if you put 00. 00 is at 001K, that's this thing, and then you do cross it with OC0. This is the second term is 0, so you'll have to cross it with L1 C1 divided by 2, L1 S1 divided by 2, and 0. So you take the cross product of these two, and you get a negative one. I doubt that. Oh, you might get a negative sign because it's a cross product, right? Cross product gives you. So in MATLAB, right? If you do cross this vector times this, I'm claiming that you get this. So try. do cross, I think this will work. If you do cross this comma cross 001 comma, you might have to do transpose something like that, but if you do cross you should get that, and you should check me on this. Okay, what I'll do is, that was a problem I was supposed to next. We'll do it next time, which will be a week from now, because next